afternoon, everyone. My name is Abrar, and this is my teammate Shahriar. So today we are gonna tell you a story about a board plane, a hidden flaw, and how we caught it. So our project investigates OPTFM, which is basically the first ever foundation model for combinatorial optimizations, and asks a simple question, which does its fancy architecture actually deliver on its expressiveness promise? So spoiler alert, it doesn't. And we can prove it. So let's start from the very beginning. Before we get into any AI thing, let's ground ourselves into the problem. MILP, you all know, the mixed integer linear program is one of the most fundamental formulations in optimization. You gotta minimize the linear objective function subject to the linear constraints, but some variables must be integers, right? That integer requirement is what makes it computationally hard or NP hard. So you see MILPs everywhere, like airline scheduling, then supply chain power grid, blah, blah, blah. So a natural question arises because exact solvers like Gorobi or Simplex might take from hours to days to solve this kind of problem on a larger instance. So can we train an AI model to predict, look at a MILP and quickly predict useful information out of it? Like whether it's feasible or not, then roughly what the optimal value would be. So there's the motivation for this entire line of research. To feed a MILP to a neural network, we represent it as a bipartite graph. So that was proposed by Yes et al. In 2019. So where the constraints on the left side and the variables on the right side, so weighted by the edges, and edge connects them whenever a variable appears in that particular constraint. So each node carries a feature vector from the solver. Now we have got a structured graph that an AI can process right now, and the curves on the right summarizes that the nodes are nothing but the constraints, the rules and the decisions, and the edges carry the coefficients. And our goal is to learn useful properties out of it from this graph. The question is, how do you process it? And the answer is GNNs, or graph neural network. So GNNs work through message passing. So each node collects information, neighbor information, and updates its own information based on what it has learned so far. And after several iterations or rounds, you've got to pull everything into a single graph fingerprint, which I call graph embedding. So the crucial detail is at the bottom. Every step uses symmetric aggregation, like summation, mean, or max over the neighbors. So the order of neighbors here doesn't really matter, but the collection matters. So this determines the fundamental expressiveness ceiling. So here is where we got. To understand that ceiling, we need to know about a classical algorithm from 1968, which is called the Lehman test, or 1WL test for short, which we will consistently use throughout the whole presentation. So it plays essentially the same game as GNN does. So what this test does is to color each node by its features, then iteratively refine, which that means that each node gets a new color based on its own color combined with its neighbor's colors. And if two graphs end up with the same color histogram, then 1W test says that, hey, look, both graphs are the same. So the fundamental theorem from Su et al. And Morris et al. Says that any message passing GNN is at most as powerful as the 1WL color refinement test. So if 1WL can tell two graphs apart, then no GNN can. So Chen et al. Actually extended this concept to bipartite graphs in 2023. So what he said that if two one equivalent MILPs can have different feasibility, so he showed that two one WL equivalent MILPs can have two different feasibility. So that means graph-based optimizer can be wrong about the most basic question in optimization. What is that question? Is the problem even solvable or feasible? So here is what that blindness looks like. So these are the two pair families we constructed. On the left, you can see that one big loop where 12 different nodes are arranged in a big cycle. And on the right, three different disconnected or disjoint loops you can see. And each of them are like 4 cycles. But here you can see that all have the same features and same degree everywhere, same features and same 1WL histograms they will produce. But they are not actually the same because one is connected and one is disconnected. They are structurally different. And family 2 on the right side, you can see that connected cubic graph versus 2 disconnected K3 by 3 1. They are structurally independent from family 1. So we verified all of these pairs programmatically, and 1WL equivalence confirmed, non-isomorphism also confirmed across 14 different scales for family 1 and 1 for family 2. So 15 pairs in total that will be explained by Shahriar later. So this is the landscape when OPTFM arrives at Munich. So the first foundation model for combinatorial optimization. So the authors actually explicitly motivate their architecture as going beyond the local interaction structure of standard GNNs. So the problem is that there's a direct claim about escaping the limitation we just described in my earlier slides. So what does OPTFM add? Nothing but the global linear attention. So every node can see every other nodes, not just its neighbor, and the cross attention with edge weights, which means the constraint against attend to the variables and variable to constraints, and the parallel bipartite GCN branch, which is basically the MPNN, which I will talk about later. Then virtual global nodes using pretrained checkpoints. So sounds pretty impressive, right? But here is the gap. The paper provides no theorem about the expressiveness and no test on the known indistinguishable pairs. Sorry. The claim is unverified, so that's the gap our project fills. So here's the hierarchical architecture of the OPTFM model. So you can see input projection, self-attention for the variables to variables, constraints to constraints, along, which is done by the HG former linear attention, then cross attention, variable attention to constraints along with the edge-weighted matrix, edge-weighted message, then parallel bipartite GCN layer, which is the message passing layer, then fuse and pull, which is the convex combination and the symmetric pulling. So every component is a multi-step function. So that's the DNA of 1WL bound. So our research question is quite direct. Does OPTFM's multi-view cross-attention architecture actually escape this expressiveness bound, or is it still fundamentally similar like the standard GNN? So our approach combines theory and experiment in practice. Like we prove it mathematically with a theorem which is backed by 5 different lemmas per component, and we test it empirically on 15 verified on-WL equivalent pairs and 6 different, not different architectures, but yeah, different components. And we probe the frozen embeddings for the structural information and verify the test is falsifiable using the positive control. So now here is where the story gets a little bit interesting, and honestly that's what taught us the most. So our March proposal used MILP pair from the literature. So we got like cosine similarity. We ran the experiments and got cosine similarity of 1, and that looked good to us, like confirmation. So, but something really nagged us. Then we ran the sanity check and asked ourselves, is this pair actually non-isomorphic? So we ran the brute force permutation search over all the variables and constraint nodes. So both MILP are feasible. We found like explicit permutation, like both MILP are feasible and not one feasible, another infeasible as claimed. So our result was completely meaningless here. So we caught this, like then we built 2 corrected pair families from scratch and rerun everything. So the lesson was that cosine similarity 1 on an isomorphic pair tells you nothing about the expressiveness. You need genuinely non-isomorphic pairs. So let's get to the main result. Like theorem 1 says that for any weights theta of the full hierarchical OPTFM encoder, if two feature level bipartite MILPs are 1 WL equivalent, then full graph embeddings must be exactly equal, not identical, but exactly equal, exact match. So this holds for any positive weight settings, not only for the, not just the pre-trained checkpoint. So training cannot escape this bound because this bound is architectural. So 5 lemmas, one per component. It starts from the linear attention layer. Each are the components of OPTFM. So linear attention uses the summation over key value pairs, which is basically the symmetric function, then symmetric operation, and then pass attention layer with edges, which basically the weighted sum over the neighbors, symmetric operation again. Then bipartite GCN, which is the standard MPNN, and Suetel proved that it is 1 WL bounded back before. And then it comes to fuse and pull, convex combination again, and then symmetric multiset function. And so virtual global nodes, that was the core novelty of OPTFM. So that is the mean of features. So symmetric function of something on WL cannot distinguish again. So you chain them together and the theorem follows like this. So let me just give you the intuition about it, not math. So just notate without any notation. So two bags with the same collection of fruits always weigh the same, no matter how fancy or clever your weighing scale is. So every OPTFM component aggregates using the summation or symmetric operation methods. The sums cannot distinguish bags with the same content. So the core insight is going global with attention doesn't help if the aggregation is still the symmetric sum, right? So the glasses are fancier, but the lenses have the same blind spot. Yes.
So before the result, let me ground the setup. So in the upper left side, we have the two family of our experiment. So family 1 have 14 pairs with one single loop and k disjointed a small loop, and family 2 has 3 regular cubic pairs. So in total, we have 15 pairs. All pairs are non-isomorphic and 1 WL equivalent. And the pictorial view of our family is actually shown in our previous slide. And in the right, we have the feature specification. So we have 9 variable features and 1 constant features. And at the bottom, we have our data set. So we have 800 random bipartite MILP. And we have 420 instances of 1 WL equivalent MILP. So this is actually the full weight. We have 6 architecture in the left. So you can see it starts from the SG former plus GCN pre-trained checkpoint, and we also have the SG former plus GCN with the initial random initialization, and then we have 3 ablations like transcop only, GNN only, and simple GCN, and the very last is the full hierarchical OPTFM. So these are our 6 architecture, and in the right we have the transformation of our input features. So we have the baseline virtual global node, then we have the LP primal, LP reduced, LP primal dual, RNF, and the very last one is RWPE. I will describe the RWPE later. And in our analysis, we use the metrics like mean cosine, which helps us to identify the similarity between the pairs. We have the fraction of exact matching embedding. We have the bootstrap confidence interval. And for the probe battery, we use the R-square for regression and accuracy minus majority for classification. So here is our very first empirical verification. So we have tested all the 6 architecture on 15 pairs with the input features. And if you can see, the SG former plus GCN pre-trained initialization provide us mean cosine of 1. So it beat identical and 100% exact match. And same goes for the SG format plus GCN and all the remaining 3 convolution, and also for the full hierarchical OPTFM. So all of these provides mean cosine equal 1 and 100% exact match. So the bottom line here is the model does not say they are very similar. it says like bit for bit identical like floating point vector. So the model actually produces the exact same output for two structurally different graphs. So here for the second result, as we said, like virtual global node can produce a better learning in our analysis. But what we did here, we implemented the OPTFM's own virtual global node transformation, exactly taken from their source code and applied our 15 pairs. And as you can see, the result shows that every pair in every architecture provides mean cosine equal 1. So virtual global node does not help us to understand the difference between the two graphs. So now one can say like no method can distinguish this pair. For that, we actually propose, our positive control is random walk positional encoding. So what we did here, for each node, we simulate a random walk and compute how likely I am returned to my initial starting point after else step. So if you can see, for the bigger loop, the 4-step return probability is 3 by 8, and for a small loop, it's 1 by 2. So it's completely different numbers. So every architecture, like what we did here, we inject this probability information at the initial level, and then do the similar experiment what I described before. And here is the right side provides the results. So you can see the three models actually reduces their mean cosine from 1 to less than 1. So previously it was 100% exact match. Now it's actually 0% exact match. So the model actually partially tried to learn the difference between the two graphs. So this actually provides that our test is actually falsificable. So now we do.
We're gonna have to wrap up soon.
Okay. So I will say this is actually the final picture. So in the left side you can see our 6 architecture, and we have the first 2 column actually says the default OPTFM base and virtual global node. So there are even no color difference. So 2 different model, but it says that their structure is exactly same. But when we actually inject the other like LP primal, LP dual, or RWPE, the color actually changes. So it starts to predict the difference between the 2 models. And the right side actually provides, no matter how we scale, the mean cosine with the default OPTFM remains the same. But when we actually inject the RWPE, it actually gives us the real picture. So to wrap up, I would like to say we think that this kind of expressiveness auditing is very valuable for the ML for optimization community, because if you do not know the model's blind spot, you cannot fix them. So that's all. Thank you for your listening, and we're happy to take questions.
That's awesome. Questions?
Yes.
So I'm wondering what's the input of this foundation model? How can you get a unified representation for this model?
Sorry.
So what's the input of this foundation model?
Oh, so the inputs are the variables and constraints shown in the MILP bipartite graphs, but
Are they described in natural language or?
Sorry?
Are they described in natural language or
so
other form?
these are provided as the graph form, bipartite graph. So, this is what they are doing. But what we are suggesting is that, let me just take a second. What we are suggesting is that if we just, these are the like variable features, all that MILP has for the variables. But at the initial stage, you get these features from the solvers, like 0 to 5. But these features can only be obtained from the solver 6, 7, 8. So these features are always 0, even if you get the pre-trained embeddings. So we are utilizing these blank slots as our target. So we are injecting we are injecting exactly this information. For example, just okay, just let me tell you. LP primal, LP dual, or randomized noise, or RWP. You are injecting these input features as the into the input feature into those slots, blank slots, as the enriched information, so they can learn the structural difference. So this is our approach.
Okay, I think we're gonna have to move to the next one, but you can always grab these guys.
So you can just drop your questions anytime. I know you have got many questions.
Thank you very much.
Yeah.